So whenever you're writing JavaScript, you're constantly creating things, right? Objects, functions, all sorts of variables. It's a whole universe of data. But have you ever stopped to think about what happens when that data isn't needed anymore? It doesn't just poof, disappear. Nope. There's this silent, automatic process working behind the scenes, kind of like an invisible housekeeper for your code's memory. So today, let's pull back that curtain and meet JavaScript's garbage collector. And really, this is the big question, isn't it? Your code is making stuff all the time, but what's the cleanup crew look like? How in the world does the JavaScript engine know for sure that it could get rid of something to free up that precious memory? Well, it turns out it's a core part of the language that just happens, all governed by a very clear set of rules. And that's what this is all about. You see, unlike some other languages where you're the one who has to manually clean up memory, JavaScript just handles it. It does its own automatic cleanup, and honestly, it does it so well that most of the time we don't even have to give it a second thought. And the hero of this whole operation is the garbage collector. Just think of it as this little process running in the background inside the JavaScript engine. Its entire job is to keep an eye on all the data we're making and figure out what's become useless or unreachable. As soon as it finds those things, it swoops in, clears them out, and makes that memory available for new stuff. So, how does it decide, what's trash and what's treasure? It all comes down to one single, incredibly important idea: reachability. Seriously, if you can get your head around this one concept, you've basically cracked the code on JavaScript memory management. So what does reachable actually mean? Well, it's pretty much what it sounds like. A value is reachable if your code can still get to it. As long as there's a live wire, a valid path, from your running code to some piece of data, the garbage collector knows hands off. That data is safe and sound, guaranteed to stay in memory. Now, this idea of reachability has to start somewhere. There's a set of values that are just inherently reachable, no questions asked. We call these the roots. Think about stuff like your global variables, or the function that's running right this second, and all the other functions on the call stack. The garbage collector starts its search from these roots. And from those roots, this whole web of connections spreads out. Every other piece of data in your program is only considered reachable if you can trace a path, a chain of references, all the way back to one of those roots. It's like an anchor chain. As long as it's connected to the ship, it's not going anywhere. Okay, enough theory. This stuff is way easier to understand when you see it in action. Let's look at some actual code, because that's when it really clicks. We're going to check out a few quick examples of how objects can lose that link to the roots and become unreachable. Alright, here's a super simple case. We make a global variable called user and we point it to an object. Since user is a global variable, it's a root. That means the object with John in it is directly connected to a root. It's reachable, it's safe. Easy enough? But now, look what we do next. We set user to null. We've just snipped the wire. The one and only connection from our root to that John object is gone. Just like that. And that's the key moment. That object is now an orphan, just floating in memory. There is absolutely no way for our code to get to it anymore. It's become unreachable. So the next time the garbage collector makes its rounds, it's going to see that orphaned object and, poof, sweep it up. The memory is now free. Okay, but what if more than one thing is pointing to the same object? Let's say we create our user just like before, but then we also create another global variable, admin, and point it to the very same object. Now our object has two lifelines back to the roots. So what happens now if we cut the first link by setting user to null again? Well, this time, absolutely nothing happens to the object. Even though one path is gone, it's still got that other path through the admin variable. It's still reachable, so it stays right where it is. Now for the really interesting one. Let's imagine a more complex setup. We have a family object. Inside, it references a mother and a father object, and they even reference each other back. They're all linked up in a little group, like an island. So what happens if we cut the only bridge to that island? What happens if we set family to null? And this is such a crucial point. The objects on that island are all still referencing each other. But here's the thing. Because the entire group has been cut off from a root, they are all unreachable. Those internal links can't save them. The whole island is now considered garbage, and it's all going to get swept away. So we know the rule is reachability. But how does the garbage collector actually figure this all out? Well, the most common algorithm that JavaScript engines use is a really clever process called mark and sweep. Let's peek under the hood. It's basically a two-step dance. First is the mark phase. The collector starts at all the roots and marks them as being alive. Then it just follows every single reference out from there, marking every single object it can get to. It fans out through the whole memory graph. Once it's marked everything it can possibly reach, the sweep phase begins. It just goes through all the memory and gets rid of anything that doesn't have a mark. I love this way of thinking about it. Imagine the garbage collector just dumps a huge bucket of paint on all the roots. That paint is going to flow down through every single reference, staining everything it touches. At the end, anything that's still clean, anything the paint didn't reach, is garbage. Time to throw it out. Okay, at this point, you might be thinking, this is cool, but if it's all automatic, why do I really need to know this? And that's a fair question. But understanding this, even just at a high level, really helps you think about your code's performance and, more importantly, helps you avoid nasty memory leaks. And you gotta know, modern JavaScript engines are incredibly smart about this stuff. They do all sorts of fancy optimizations, like generational collection, works on the theory that most objects die young, so it checks new ones more often. Incremental collection breaks the big cleanup job into tiny little pieces, so your app never feels like it's freezing. And idle time collection is super clever. It waits for your CPU to be chilling out before it does its work. It's a really sophisticated system. All right, let's wrap this up. What are the big takeaways here? Number one, this whole thing is automatic. We can't force it, we can't stop it. Number two, the golden rule is reachability. If you can get to it from a root, it stays. If not, it's gone. And finally, remember that unreachable island. A whole bunch of objects pointing to each other doesn't matter if the whole group is cut off from the world. So I'll leave you with a final thought. Now that you know how this invisible housekeeper does its job, you can start looking at your own code with new eyes. Think about stuff like event listeners you forgot to remove, or maybe some cache data that never gets used again. Where are those accidental, unreachable islands hiding in plain sight in your code?